Second derivative test for local extrema. Suppose that f is a function, f prime and f double prime exists on the interval AB. C is in the interval AB, and f prime at C equals 0. Recall f prime at C equals 0 tells you that C is a critical value. If f double prime at C greater than 0, that means the function concave up within this interval. F at C is a local minimum. For f double prime at C less than 0, the graph concave down, then f at C is a local maximum. If f double prime at C equals 0, then the test fails to give any information about local extrema. The quick tip for this, for the function concave upward, if C located in that interval, recall if C is the critical value from the f prime C equals 0, we have the horizontal tangent there. So the point C is the local minimum value within that interval. For the f double prime less than 0, the graph concave down, and the point C located in that interval, and the slope of the tangent line at the point C is 0. Therefore, the C is the local maximum for the function within that interval. And you see the graph. C is the local mean where the graph is concave upward. C is the local max where the graph concave downward. In general, the principle being applied in the second derivative test is very simple. If f double prime defined at a local maximum, a curve concave down. The other way, the curve is concave up. The C is the local mean. In this example, the function f of x equals x to the fourth minus 18x squared. Part A, locate the local extrema. Part B, locate the point of inflection. Locate the local extrema using the second derivative test. We're going to find the critical value C, which is from f prime at C equals 0, and then whether the function, the second derivative at C greater than 0, or the second derivative at C less than 0 or not. If greater than C, recall the graph concave up and C will be the local mean. If f the prime less than 0, the graph concaves down. The C will give you the local maximum. Let's get started with part A. Find the critical value. F prime at C equals 0. So f prime of x equals 4x to the third minus 36x. Factor the 4 and x out. We have x to the second minus 9. Factor more to get 4x, x minus 3 times x plus 3. Now we get three values as a critical value. X equals 0, x equals 3, and x equals negative 3. Three critical values. Let's find the value and set on the side. So f at 0 equals 0. F at positive 3 equals 3 to the fourth minus 18 times 3 to the second, which is negative 81. And f at negative 3 equals negative 3 to the fourth minus 18 times negative 3 to the second, which is the same value, negative 81. Next, we're going to determine the concavity of the function at the point negative 3, x equals 0, and 3. Let's use a blank area here. X equals 0, negative 3, and positive 3. And the first derivative, which is 4x to the third minus 36x. To determine the local max, local min using the second derivative test, we move on to find the second derivative, which is 12x to the second minus 36. So at x equals 0, f double prime at 0 equals 12 times 0 minus 36, which is less than 0. The graph will be concave downward, less than 0. So x at 0 gonna give you the local maximum at x equals negative 3. F double prime at negative 3 equals 12 times negative 3 minus 36, which is 72. No, negative, positive 72, which is greater than 0. Greater than 0, the graph concave upward. And the point x equals negative 3 will give you the local minimum. For x equals 3, f double prime at 3 equals 12 times 3 minus 36. This time give the same value. This is power 2. I'm sorry. Power 2, power 2, power 2. So with the power 2, the quantity of the first term is positive and larger than 36, gonna give you the sign positive sign, the same as at x equals negative 3. So this one, again, the graph concave upward. The point negative 3 and positive 3 will give you the local minimum value. So at negative 3, negative 81, we get the minimum point, 0, 0, get the maximum point, and 3, negative 8, get the minimum point. Next one, we're going to consider the inflection point. So to find the inflection point, we're going to find a hypercritical value. Hypercritical value can be found by setting f double prime be 0. So our f double prime for this case is 12x to the second minus 36. Let it be 0. Factor 12 out. Have 12 times x squared minus 3 equals 0. That means x squared minus 3 equals 0 gives you x equals square root 3 and x equals negative square root 3. So we have two hypercritical values. And to find out the sign of f double prime, whether it changes from one to another or not, from the left to the right side of each hypercritical value. Negative square root 3, where f double prime is 12 times x minus square root 3 times x plus square root 3. And on the right side of square root 3, any value that's greater than square root 3 gonna give you the positive sign for the second derivative. Any value in between negative square root 3 and square root 3, for example, 0, gonna give you a negative sign of the f double prime. The value less than negative square root 3, for example, like negative 2 or any number that's easier to compute, on the left side gonna give you a positive sign for the second derivative. That means the sign switch from one to another at both hypercritical values. So then both of them give you the inflection point. To find the order pair, so the function at negative square root 3, plug it in the original function, we should get negative 45 for both of them. Therefore, we have 2 points of inflection. Gonna be the order pair negative square root 3, negative 45, and square root 3, 45. And when we see the graph, we see the critical values at -3, at 0, and 3, where the slope 0, or the horizontal tangent at those 3 points. And the hypercritical at -√3 and √3, where the graph changing from concave upward to concave downward, and from concave downward to concave upward.